everyone, welcome back to this channel. So today we'll be deriving mean square speed formula. In the previous video, we discussed on how to derive ideal gas constant, or not ideal gas constant, ideal gas equation, where we use the concept of PV over T equals to constant. And finally, we came up with two different formulas, which is PV equals to nRT and PV equals to NkT. So today, we're going to dive deeper into how do we derive mean square speed equation. Okay, so now we're going to use the concept of pressure. So we know pressure equals to force over area. Okay, so now I want you to consider a molecule here with mass m, and it has a velocity at x component known as cx. I'm not trying to say that the gas molecule only moves in x direction. The gas molecules moves in all three dimensions, in x direction, y direction and z direction. Here I'm just giving an example because you're going to derive a formula, so I start with an example where the molecule is moving in x direction. It will be easier to derive as we go on. Okay, so now consider we have this gas molecule with mass m and x component velocity of cx. So what is force? So we know force is mv minus mu over t. What is this? This is change in momentum. This is what we call change in momentum. And this is the time taken for the collision. Okay, so now imagine this gas molecule travels this way and it hits at this particular phase. Once it hits, it's going to reverse direction and move this way. Am I right? So first it moves this way. After that, it's going to reverse direction and move this way. In this direction, it's going to be mcx. C subscript x. Now why is it mcx? Because we know momentum is equals to mass times the velocity. So we have our mass here, we have our velocity here. Now, the moment it reverses direction, it collides with the face of the wall, it collides with this particular face, and then it's going to reverse its direction, right? You're going to have negative mcx. Why negative? Because you are reversing direction, and momentum is a vector. Very important. So, since momentum is a vector, direction is very important. So, it is negative mcx. Okay, now we got the force. In terms of momentum, we got the change in momentum where we find mcx, and in reverse direction it's negative mcx. How about the time? Well, we know velocity is equals to distance over time, or speed is equals to distance over time. The distance traveled by this particular gas molecule is actually 2L. Why? Because you see, these gas molecules move this way, travels in this direction, it travels L. And go this way, it's going to travel another L. So L plus L gives you 2L. Since it's a cube, all sides you'll have the length L. They'll have the same value of L. Okay. 2L. Time is what we are going to find. How about velocity? What is our velocity? Our velocity is c subscript x. So that means our time is actually 2L over cx. Now can we sub in this one and this into the pressure formula? Of course we can. But before that, we start slow. We'll do it slow by step. We sub inside the force formula first, then we will go inside the pressure formula. Okay, so our force will now be equivalent to mcx minus negative mcx over, what is your time? 2L over cx. Okay, so we do the math. You can cut this. mcx squared over L. So we got our force. Now we know pressure is equals to force over area. So we can further substitute this inside the force over L A. Okay, I think I better write as AL. We have a L here, and you have a A from here to here. Okay, what is AL? AL is actually volume, right? So we can further write it as mcx square over volume. Okay, this is for one gas molecule. Now let's say I have n number of molecules. If I have n number of molecules, what will my total pressure be? My total pressure would be equivalent to mcx1 square over V plus mcx2 square over V, so on until you have mcxn square over V. Why is it x1, x2, xn? Because now you have a lot of molecules inside. All the molecules are going to move at a different speed. Oh, I forgot to mention. You might be thinking, why here I use the same speed? Because between collision, the speed of the gas molecule between collision are uniform. I repeat again, between collision, let's say with this face of wall, between collision, the speed is uniform. However, when it just randomly move, because we know based on ideal gas, they move randomly. When they just randomly move around here, their speed are random as well. That means they have different speed. That is why I denote them as 1, 2, until n. So each molecules have different speed as they move randomly. So if I rearrange this formula, I can actually take out mv, because they are like terms, all the value has mv. So I can take out mv, and I will have cx square 1 plus cx square 2 until cx square n. Okay, guys, idea so far. This is for one gas molecule. This is for n number of molecules, when you have n number of gas molecules. Okay, alright, now this is where we introduce the concept of mean square speed. So what is mean square speed? Let's first start on understanding what is average. Average is basically mean. So what is mean? You take the summation of the total values, then you divide by the number of values. For example, I have 3, 6, 7. What is the mean? You take 3 plus 6 plus 7, divide by 3 because there are 3 numbers. Right? Same thing here. Now, imagine in terms of gas molecules. So, how do we calculate the average of the speed of gas molecules? Or in other words, mean square speed of gas molecules. So, what will you do is, you have cx square 1 plus cx square 2 over n. This will be your mean square speed. Am I right? Why is it not mean speed but mean square speed? Because the speed has square. You realize? So this will be your mean. You divide by the number of molecules, you'll get your mean. So now, in order to implement this inside here, what we have to do is, we have to add n in front here. Then, you put in your mean square speed. Okay, I'm going to erase this one here. Okay. Your number of molecules this is how you introduce mean square speed. Now why I introduce n here? Because the moment I cancel out n and n here, because it can be cancelled out, you realize I'm going to get exactly the same thing up there. So I'm not changing the equation, I'm not creating anything, I'm just introducing mean square speed, but when I cancel out, I'm going to get the same thing up there. The purpose we do this particular step is to introduce mean square speed. So now I can write it even better, nm over v cx square. You can write it like this, where your cx square, this one, is actually over, and I just write it better by just saying it is cx square. Okay, nice. We got our formula for mean square speed. Okay, I think it's better I highlight it. Okay, let me use pink highlighter. Okay, so you can see this. So first formula for mean square speed. Now let's go in detail. Like I said earlier, doesn't mean that the molecules are only moving in x direction. They are also moving in y direction and z direction. So how about their mean square speed? On average, all of them will have the same mean square speed on average. Oh, also, I made a mistake somewhere here. I hope you realized it. In physics, I believe in maths as well, mean usually denote using this sign. These two signs. This is what we call as mean. So at here, I cannot use this. I must put this. Yeah, now it is more accurate. Yes, now the formula is more accurate. You must denote it using that, using this sign. This sign indicates mean. So coming back to the story, on average, the mean square speed in x, y and z direction will be the same. Why? Okay, let me give you an analogy. Okay, for instance, you have a room full of people, and there are 4 exit doors in each of the room. That means there's 4 doors at the end where you can go out. Suddenly, there was a fire in the middle of the room. What happened to all the people here? They'll start running around, right? They start running around. Is there a reason for these people to only move out this particular door? Is there a reason? No. They'll move randomly. Some will go here, some will go here, some will go here, some will exit this way. But on average, at each door, the people will exit equally. On average, the people will exit on each door will be the same. In other words, for example, gas molecules, you have inside gas molecule. Is there a reason for the gas molecules to only move in one direction? Is there a reason that it only has to move in x direction? No. Unless there's a force. This is ideal gas. Unless you're telling me someone is pushing this gas molecule to only move in one direction, and then yes, the average mean square speed will not be the same. But it can move randomly. So on average, in x, y and z direction, on average, they will be the same. Same thing goes to this room. On average, on each door, there will be the same number of people exiting the room. Remember, I repeat again, I said average. On average, there will be the same number of people exiting each room. Unless you are telling me, again, there's a force. Someone is pushing you to one door, then the average will run. You won't have the same. Regardless, otherwise, if no one is pushing you, you will move on average equally in all x, y, and z direction. X, y, and z direction on average will move the same. This is something called symmetry. And inside ideal gas, definitely there's no force inside for you to push in particular one direction, right? That's why we come up with this equivalent form. The mean square speed in x and y and z direction are the same. Okay, so now what do we do with this information? So since they are the same, what will be the sum of the mean square speed, or you can say the total mean square speed? Now we have x, y, z direction. What is the total of the mean square speed? So I'll denote this as c square equals to, you will get cx square plus cy square plus cz square. This is the total mean square speed. Now since we have already discussed the fact that they are equal, so we can all write it as cx square plus cx square plus cx square. So what will you get? You will get 3 cx square. This is what will you get. Okay, so far I got it. So on average, in each direction, they will be equal. On average. Okay. Now, remember we first derived this equation here? So we can actually substitute this inside here. Now how do we do that? Since we have cx square here, we have cx square here. So let's make cx square as a subject. So 1 over 3 c square equals to cx square. Now let's substitute inside this formula. Okay, let me use a different color. P equals to n m over v. Our cx square is now 1 over 3 c square. So now how do we write it better? Let's write it better. We can write it as n m over 3v c square. Okay, so we can actually bring our v here. You can actually do that. Okay, why I'm doing that, I'll show you in a while why I'm doing that. PV equals to 1 over 3. You can actually write 1 over 3 is better. 1 over 3 nmc square. Okay, we have finally come to our mean square speed equation where PV is the subject. Now, look at the subject. Is it quite familiar to you? Remember, in the ideal gas equation, we derive something called PV equals to NkT. Can we make use of that? Of course, we can. Now, let me use another color. Okay, let's be colorful today. Okay, so let me write here PV equals to NkT. Can we equate them? Of course, we can equate them. So let's equate them. So you will get NkT equals to 1 over 3 nmc square. N and N you can cancel out. So you will get KT equals to 1 over 3 mc square. Okay, so now when we talk about mean square speed, we can think about kinetic energy, right? Kinetic energy, because kinetic energy involves speed. And we know the formula of kinetic energy is 1 over 2 mv square. So realize this one and this one, they almost have the same form. So what can we do to make it the same form? Okay, we bring the 3 to the other side. 3 kT equals to mc square. Now what we do, we divide both sides by 2. So you'll get 3 over 2 kT equals to 1 over 2 mc square. Is it the same form now? Oops, okay, I think it stood up. Is it the same form now? Yep, it is the same. So we can actually write the kinetic energy of all the molecules Oops, don't forget something. The mean kinetic energy of all the molecules is equivalent to 3/2 kT. This is the mean kinetic energy of the molecule and I equate to 3/2 kT. There you go. You finally got a formula. From pressure, we come all the way here to find the total pressure. Then we find the mean. Then we use the ideal gas equation, we combine, and we get the kinetic energy of all the molecules. How beautiful is that, right? Okay, now what if they ask total kinetic energy? This is kinetic energy, the mean kinetic energy of all the molecules. But in other words, this is actually for one molecule only. Why? Because you see, this mass here, right? This mass is mass of one molecule, right? So this is actually the kinetic energy for one molecule because this mass is one molecule mass. If they want total kinetic energy, then you have to add N. This is number of gas molecules, total. Because this is for one, you only uses one molecule mass. So ideally it's for one molecule. The mean for one molecule. Now if you want the total, you have to add N, which is number of molecules. Okay, alright, just nice. We are actually done here. Just one more tip, one more small information that might be useful later on. Ideal gas has no potential energy. For your information, ideal gas has no potential energy because the intermolecular forces are negligible. That's why we say ideal gas has no potential energy. So what will be the total internal energy? So, okay, internal energy, we know, I'm just going to put as IE, is where kinetic energy plus potential energy. Right? So for ideal gas, what will be the total internal energy? Your total internal energy for ideal gas, yeah, is actually just kinetic energy. Because your PE is 0. Why 0? Like I said, the intermolecular forces between molecules are negligible, right? For ideal gas. Remember, yeah, for ideal gas. So, your total internal energy is just kinetic energy, which is just basically 3/2 NkT. That's it. Yeah. Alright. Okay. So, that's about it. This video, you learn about mean square speed. Also, don't panic if they ask suddenly for root mean square speed. If they ask for root mean square speed, sometimes they'll give you like this. CR.M.S. This means root mean square speed. Don't get panicked when they ask that. Basically, this is mean square speed means root means you square root the mean square speed. Okay. Another important point. This one is not the same as this, yeah. This is you square the mean, you square the speed, then you mean it. You average it. This one, you add all the speed, you mean, then only you square it. You will not get the same value, yeah. Remember, it's mean square speed. You square the speed, then you mean it. You average it, okay? Alright, so that's about it for today's video. I think today's video is going to be a bit longer because we derived a lot of things today. No worries, you can watch back the video, okay? If there's something you do not get it, try to watch back slowly. I believe at the end of the time, you will actually understand on how it works. So now that we have actually derived mean square speed and ideal gas equation, you will be now prepared to answer thermodynamics question, because this is a bit of the basic things that we need in the next video where we'll soft thermodynamics question. Okay, so that's all for today. Thank you for watching. If you have any questions or you want me to solve some other papers or anything you want me to share, don't hesitate to let me know in the comments. I'll always try my very best to help. So see you again in the next video. Bye bye.